In this problem, we're diving into a beautiful and classic problem from the 1992 International Mathematical Olympiad. This is a functional equation, a type of problem that asks us to find all functions that satisfy a given property. In this video, we have the IMO 1992 problem 2. We have a functional equation, which is a type of problem that asks us to find all functions that satisfy a given property. The problem is find all functions f from the real numbers to the real numbers, such that for all real numbers x and y, f of x squared plus f of y equals to y plus f of x squared. Our goal here is going to unravel the properties of f until we can determine its exact form. The first step to fully solving this problem is proving the function is bijective. Bijective means it's 1-to-1 and onto. So basically it's both injective, which is 1-to-1, and surjective, which is onto. To prove surjectivity is easy. If you fix x to be some constant, say x equals to c, the expression becomes y plus f of c squared. As y can be any real number, the expression y plus constant can also produce any real number. Since this expression is the output of our function f, it means that the range of f is going to be all real numbers. So we have f is surjective. To prove the injectivity 1-to-1, you need to show that if f of y1 equals to f of y2, so we assume that f of y1 equals to f of y2. Then it must be that y1 equals to y2. Let's assume that first. So from the original equation, we have f of x squared plus f of y1 equals to y1 plus f of x squared, and f of x squared plus f of y2 equals to y2 plus f of x squared. Now, since f of y1 equals to f of y2, the left-hand side of these two equations are identical. Therefore, the right-hand sides must also be equal. So we'll have y1 plus f of y1 squared would equal to f1 plus f of x squared equals to y2 plus f of x squared. The x squares cancels out. So this will leave us with y1 equals to y2. So f is injective. Combining these two together means that f is bijective. This is a very strong condition to solving this problem. Next, I want to find the value of f of 0. Since f is surjective, we must know that there must be some input, let's call it c, such that f of c equals to 0. Let's substitute y equals to c into the original equation, so we'll have f of x squared plus f of c equals to c plus f of x squared. So f of x squared plus f of c, which is 0, equals to c plus f of x squared. So this gives us a new useful relation. F of x squared equals to c plus f of x, the entire thing squared. Let's use these two new equations to find the values of c and f of 0. So from b, we can plug in y equals to c. We'll have f of c equals to c plus f of 0 squared. Since f of c equals to 0, so we have f of 0 equals to c plus f0 squared. Now let's go back to relation A and set x equals to c. So we'll have, let's apply the function f to both sides, knowing that f of c squared equals to c. F of c squared equals to c plus f of c squared. So then we'll have f of c squared equals to c, because f of c equals to 0. Then, knowing this, we'll have f of c squared equals to f of c. Using relation B on the left side with y equals to c squared, you'll have c squared plus f of 0 squared equals to f of c. And since we know that f of c equals to 0, we know that c squared plus f of 0 squared equals to 0. The square root of any real number is non-negative. The only way the sum of two non-negative numbers can be 0 is if both numbers are 0. Therefore, c squared equals to 0, which means c equals to 0. F of 0 squared equals to 0, which means f of 0 equals to 0. Now we can derive the final form of the function. We've made a huge breakthrough, f of 0 equals to 0. So let's see what relations A and B have become. Relation A was that f of x squared equals to c plus f of x squared. Relation B was that f of y equals to y plus f0 squared. So basically the relations have now become f of x squared equals to f of x in parentheses squared, and B has become f of y equals to y. Let's substitute f of x squared equals to f of x squared back into the original equation. So we'll have f of x squared plus f of y equal to y plus f of x squared. We can let z equal to x squared. Since x can be any real number, z can be any non-negative real number, z greater than or equal to 0. The equation becomes f plus z plus f of y equals to y plus f of z. For all z greater than or equal to 0, y is a real number. We know that f of y equals to y. This means we can replace y with f of t for some t, and we get f of t equals to f of t, or simplifies to f of t equals to f of t. More usefully, let's substitute y equals to f of t into our last equation. So we'll have f of z plus f of t equals to f of t plus f of z. So we'll have f of z plus t equals to f of t plus f of z. This holds for all z greater than or equal to 0, and for all t is less than or equal to r, for t belongs to r. So this is almost in the form of the famous Cauchy's functional equation. We can easily show that it holds for all real numbers. If we have two negative numbers z1 and t1, we can pick a large positive number k such that z1 plus k greater than 0, t1 plus k greater than 0, and z1 plus k greater than 0. And use the property to prove that f of z1 plus t1 equals to f of z1 plus f of t1. So we have proved that f of x plus y equals to f of x plus f of y for all real y and x. So now, the solutions to Cauchy's equation can be very strange, but this extra condition constrains f significantly. So for any x greater than or equal to 0, we can write x equals to square root x squared f of x equals to f of square root x squared equals to f of square root x parentheses squared greater than or equal to 0. This means that f maps non-negative numbers to non-negative numbers. A solution to Cauchy's equation with this property must be in the form of f of x equals to ax for some constant a. Let's substitute f of x into the condition f of x squared would equal to f of x in parentheses squared. So basically, we'll have a of x squared would equal to ax squared. So ax squared equals to a squared x squared. This must hold for all x. So it implies that a equals to a squared. Then a squared minus a equals to 0. A times a minus 1 equals to 0. A equals to 0 or a equals to 1. The first case, a equals to 0, then f of x equals to 0 for all x. We can check this into the original equation. We'll have for a equals to 0, the left-hand side equals to f of x squared plus f of y equals to f of x squared plus y, which is x squared plus y, equals to the right-hand side, which is y plus f of x squared equals to y plus x squared. And this is for a equals to 1. So it works. We have found one solution. However, for a equals to 0, then f of x equals to 0 for all x, while a equals to 1, f of x equals to x. However, in a equals to 0, the right-hand side and the left-hand side are not equal because we will have 0 equals to y, which is not true for all y, so this does not work. So after breaking down the solutions and properties of the function, we found that there's only one function that satisfies the condition for all real numbers. And that means that the only solution is f of x equals to x. And that is how you solve this challenging IMO problem.